Hey guys, my name is Adrian and welcome to Organic Chemistry 1, Part 10 of these recorded sessions. Today we'll be going over for most of y'all Chapter 10 and in general alkenes. So we already saw a little bit of alkenes a couple videos back, but this time we'll be focusing on reactions involving alkenes and not just elimination, right? So here's our agenda and it's gonna be pretty quick, pretty short, shorter than the other ones. So we'll be going over alkenes. You guys are already familiar with that, but we'll rehash fatty acids, which is interesting. Kind of preparing you for OChem 2 and even biochem preparation of alkenes and addition reactions. So same thing with alkanes. There's addition reactions that you should follow, and there's a new role we'll be looking into. So with that being said, let's get started with again alkenes. So alkenes, we know, and this is good to review because you don't the simplest details. You don't want to forget the simplest details, right? You don't want to kick yourself in the butt by forgetting one itty bitty detail that you for sure know, right? So we know it's sp2, trigonal, and 120 degrees, right? The hybridization, and we know restricted to rotation always, right? There's no exceptions to rotation. And that we know that we learned about monosubstitution, tri-substitution, right? With one R group and so on and so forth. So, right. So we know all this and we know the stability, things like that. So since I'm started drawing this, might as well finish it up, right? So, okay. So we have mono, di, tri, tetra, right? And where does the stability go to? And I'm going to do this in another color. Stability increases this way, right? Stability increases. So we know tetra is the most stable, mono is the least stable. So nothing too crazy. And now what's more important is that we didn't talk about the boiling point, the melting point, things like that. So all that still applies, right? We know pi bonds are weaker than sigma. Sigma bonds, making double bonds, alkenes, easier to break than alkanes, right? So we know boiling point, melting point, solubility rules apply just to kind of get that into your heads, right? Don't forget about the boiling points, melting points. Same applies, symmetry, surface area, things like that. Solubility, you know, alkenes, things like that. And alkenes, we might have to go to another one. Um, we'll have to also look at, more importantly, polarizability. Polarizability, right? So let's jump onto a new page and start off with polarizability. Why it's important? Alkenes. Polarizability. And polarizability is the you know the the likeness of an electron leaving, right? So electron leaving, right? So if it's more polarizable, more likely the electrons can be taken away. If it's less polarizable, vice versa. So as we know, alkenes come in cis trans, right? And also or EZ, right? So for here, for polarizability, if it's the higher the polarizability, ability, um, the higher the melting point and boiling point, right? And then vice versa, the lower melting point, boiling point. And now you're probably wondering, so which ones, how do we know which one's more polar, which one's more less polar? Well, that just depends on the dipole moments, right? So cis alkenes have higher polarizability than trans. And that makes sense. Trans will cancel each other out, cis kind of reinforce, right? So going through like that. And also don't forget that alkenes are nucleophiles, right? So they are electron rich. So that means they'll attract electrophiles, right? Or electrophilicity, things like that. So um, yeah, alkenes, nothing too crazy. And nomenclature, we already talked about this. IUPAC rules apply. Rules. Um, we have cis, trans, easy, um, things like that. Parent must go through double bond, right? Let's add that here. Cis, trans, or whatever. C, E, and Z. Easy, right? Okay. So nothing too crazy. We already know all these. You know, just a little review, right? Just to kind of tie everything else together. Um, so let's do some examples. And actually, before we do examples, let's go review degrees of unsaturation. So alkenes are the first to have degrees of unsaturation because of that pi bond, and we know degrees of unsaturation is just 2C plus 2 plus N minus X minus H divided by 2, right? And degrees of unsaturation um, reveals or calculates number of pi and or rings, right? And or rings. So for example, um, this has a degree of unsaturation of 2 because it has 1 pi and a ring, right? Pi and 1 ring. So that's how kind of you tell that, and just by looking at it, that's how you can tell the degrees of unsaturation without having to calculate the thing. Um, and so, okay, now that we have that, just kind of reviewing again degrees of saturation. You guys don't use this a lot, but the formula you don't use a lot, but it's good to know how many degrees of saturation just by looking. Okay, so let's do some examples. Alkenes. So one, let's do some naming. Here we go. This one, and then this one. Okay, so pause the video, take a second, and come back with the answers you got. Okay, so you should have gone to ethyl 1 heptene. And why is that? Where did we number from? 1, 2, 3, 4, 5, 6, 7, right? And so this is the ethyl group. And again, we want to go through that double bond, and this is the longest chain going through the double bond, right? So nothing too crazy. And for this one, you should have gone 1 methyl cyclo um, cyclopentene, right? Cyclopentene. So for this one, um, that's all. Nothing too crazy. We numbered this way. with the methyl group right there, right? 4, 5. And then we can do the same over here. You guys should have gone 1,6 dimethyl cyclohexene. So you guys have seen this before, and they went through here because that gives the double bond and this first substituent the lowest number, right? 2, 3, 4. Oh, I missed one. 3, 4, 5, 6. Right. So super, nothing too complex. Same rules applied. Longest chain, lower substituent numbers, go through the double bond. Right. Okay. So let's do a couple more. We have a couple more here for alkenes. Alkenes. So let's do this. Label EZ and this molecule. Okay. And then here, rank lowest to highest BP. We have this one, this one, this one. So take a minute and get me what you got. Okay. So over here, E to Z is not pertaining to the whole molecule, it's pertaining to specific double bonds, right? So in this case, this one's E, and this one is E, right? And this one is a non-none because this is there's no substituents on this other side, right? And instead it's a carbonyl. It has a oxygen instead. So there's nothing for this one. So only these two have classification, right? And our Z, let's just draw a Z just for fun, something like this, right? Okay. So over here we can even rank this, and going off of this, we have here what a no, right? Because there's no substituents over here. This is a cis or a Z, which is what we drew over here, and this is a trans or an E. So highest, lowest to highest BP. You guys should have gone the first one, the third one, and the second one, right? And why is that? We're talking about here polarity now, right? We talked about earlier about higher polarity, um, lower boiling point, so things like that, right? Or I mean, higher polarity, higher boiling point, and melting point. So this one is obviously the highest boiling point. This one over here is the one that's kind of getting canceled out, right? So things like that, nothing too crazy. Um, the Probably the biggest takeaway for this is polarity because we never used polarity before to judge the boiling points and the melting points. So polarity, the higher the polarity, the higher everything else is, right? Okay, and that's sits first. Okay, so let's go ahead to kind of a little bit preview, and it's pretty fun. This applies to real life, right? Fatty acids, fatty acids, especially for all the healthy people, right? And this is kind of like where the concept begins with healthy fats and not so healthy fats, right? So just the concept, um, you know, you're not gonna get tested on this or anything, but it's just good to know, just for your information. So we have these things called triacylglycerols, right? And they're fats. Um, the composition is RCOOH, right? And pretty much something like this is the most normal one. with like a carboxylic acid over here, right? So kind of like that, right? Whatever. It can have double bonds. It can have no double bonds, things like that. So, you know, triacylglycerols. They also called, you'll call them in biochem tags, right? And now we know fatty acids come in saturated and unsaturated. So what do you guys think this means? Saturated means no double bonds. This um, one or more double bonds. One plus double bonds. And that's because saturated is saturated with um, hydrogens, pretty much, right? So instead of double bonds, this has hydrogens taking those place. So saturated with hydrogens. Hydrogens less hydrogens, right? So kind of like, I think of it as oxidation and reduction. So obviously, if you have more hydrogens, either what did I say? Reduction, right? Reduced compared to oxidized, things like that. Um, but it's kind of like saturated, unsaturated is kind of another version of oxidation and reduction, right? And this is important because, like we said earlier, pi bonds are weaker than sigma bonds. So unsaturated fats are the healthy fats because you can break those pi bonds and break up the molecule, right? And another word for unsaturated double bonds and why they break up so much easier because they have kinks. Those kinks can be broken and then the whole molecule is broken down. So they're healthier fats because you can break them down faster, easier, things like that. And in saturated fats case, those single bonds are harder to break, right? Requiring more energy, which we don't want, right? We don't want to expend extra energy to burn down fat. We want them as fast as possible to be gone, right? So that's it. Um, and yeah, so this is why kind of just like here is the difference between between fats and oils. So fats are mostly saturated, while oils, that's why oils are good for you, unsaturated, things like that. So yeah, something to think about, when you're looking at the fats and stuff. Now you can kind of connect it to like why. It's because of those double bonds, alkenes, right? Okay, so that's just that, just fun information. This is a pretty short, um, little chapter, section, lesson thing. So I just included this just for your information. So, and hopefully you guys remember this for biochem or whatever, because you'll see this a lot. This is pretty much like half of biochem one. So, okay. So now let's get to something more, um, I guess, relevant, right? So now we're prepping alkenes. Preparation of alkene. So these are pretty straightforward. Um, let's say we kind of saw this in the elimination video, the E1 and E2 and stuff. So let's say we have that. You guys should definitely remember this, right? You guys know where this is going. Alcohols, right? We have halogens over here, and then another type of alcohol, right? So how can we make double bonds from these? Well, this one we can just CH2, CH3 to eliminate that halogen, right? Or this, right? This one, we know this is a tosylate, right? KOC, CH3, 3, right? Double bond. This one, how do we get rid of alcohols? H2SO 4, right? And then What about in the cyclic? Another. Well, this is pretty much all the same, but just different examples. You can also use POCl3 and pyridine with HCl, right? Or there's always going to be, either one. So yeah, this is the same, right? Just with alcohols, things like that. So this is where kind of don't forget these because this isn't included in the main addition reactions, right? This is preparing alkenes. So now we have alkenes. We can use our addition reactions and to make whatever we want, right? We can go back to halogens again by using halogenation, things like that. So you can do more with alkenes than with these, pretty much, right? So don't forget about these. Um, add them to your card or little sheet, things like that to kind of remember. And yeah, just have them with you. And then now we get to the real deal of addition reactions. This is where the actual um, we haven't seen these before, right? Because the last for the preparation of alkenes, we kind of saw that with elimination because if elimination reactions make pi bonds, right? But with addition reactions, this is kind of a different one. These are all new reactions. So again, let's start with our generic double bond, right? And we're gonna have 5, right? So set this up as we will, and then HX, H2O, H2SO4, X2, X2, H2O, BH3, H2O2, OH minus. Okay, I think, yeah, I left enough room. So this is what I was talking about with the just swapping it with um, a halogen, right? Or it could be in the other one. I don't want to take up too much room because we'll be writing stuff. So, and this one, same thing, but with an OH group. OH, OH, right? X2, X, X, so that's just one. X2H2O, OH, or vice versa. Okay, we'll leave that like that, actually. And this one, OH. So now, this is where it gets interesting. So we don't need to care about the names, halogenation, hydration, halogenation, halohydrogenation, things like that. But what we care about is these, this rule, Markov-Nikov. So same with Zaitsev, right? Zaitsev is double bonds forming the more um, stable formation. So tetra over tri substituted over di over mono substituted, right? So for Markovnikov, it's where the hydrogen and the halogens go. So with Markovnikov, H adds to less substituted, while the halogen or whatever goes to the more substituted, right? So this is important. H, that's all pretty much you need to know. So in this case, um, both of these are equal, so we don't really mind, right? And but so we'll do practice with those. But another thing we need to keep in mind is the anti versus um, syn addition, right? We talked about that a couple videos back, I think, where they attack from the front, they both attack from the back, or they're both on opposite sides, right? So in this first one is a mark. It follows mark. and there's no preference. It can be anti or sin, right? Anti or sin. It doesn't matter. For this one, same thing. It follows Markovnikov's rule, and it can be anti or sin. This one doesn't really matter if it's Markov or not because there's no hydrogen getting added to anything, but it is anti, right? Anti. And why is it anti? Well, both of those halogens are pretty big, right? So you're not gonna want them in the same plane. You want them to be opposite planes, right? And same thing over here, just OH and halogen group. And again, is anti. But for this one is interesting because for this one, the more substituted one goes to the OH. So this is acting as the hydrogen, right? This one acting as a hydrogen in Markovnikov's case. So, but this is still anti, right? And this one is anti Markovnikov, and this can add anywhere, as well. So yeah, that's that. This is the ones in the blue are probably the more important ones, because this is pretty easy to memorize and they're pretty self-explanatory with the HX, a hydrogen and a halogen, right? Um, H2O, OH, X2, two halogens, things like that. But what to pay attention with is how they're getting added. So anti, anti-Markovnikov, right? So pretty much the one that adds two big um, atoms, two big groups, is going to be anti, right? Because it's a more stable position. So with that being said, let's do some practice. Let's see, and it's gonna be much better with practice. So what is this? Addition reaction. Okay. So let's do these. Oh, first one, which will react okay. And I think we had this question actually, a version of it anyway. Oh, okay. I just ruined that one. This is supposed to be a single bond. I think we had a version of this question either a video or two ago about the rate. So let's see if you guys remember. Okay. And then now, let's see. Find the product. CH3, H2O2, HO minus, H2SO4, and then last one. Okay, so pause the video and answer and come back when you guys have it. Okay, first things first, this first one, what is it dealing with? Carbocation arrangement, right? Arrangement, right? And how do we know that? With HCl, we know HCl prefers elimination, right? This is what we were talking about the E1 and E2 type thing, and HCl prefers either E1 or E2. But that doesn't even matter because elimination creates carbocations, and carbocations want to have the most stable carbocation formation, right? So over here, carbocation here, carbocation there. This one is in the what position? It's just in a mono substituted, right? And same here, over here. These are both mono. So is that the most stable carbocation position? No, right? What about this one? No, as well, right? And actually, this one is mono. This one is di because we're eliminating the double bond, right? So mono di. So what about this one? Di, di. This one mono tri. So this one's tri substituted, and is the only tri substituted. So you guys should have gotten this one, right, as the fastest with HCl, because that's the most stable carbocation, and that's where it's gonna go. And now let's do a different color for the reactions. Let's do a green. So for this first one, we talked about it um, earlier, right? So everything still stays the same except for the double bond, of course. But where is everything getting made? Right, you guys should have put the OH over here because this is anti-mark, right? Anti-mark. So the OH is going to add to the less substituted. OH2 less substituted, right? And let's do another color. So what about this one? H2O, H2SO4, what is that making? OH, right? And there's two places this OH can be. It can be over here or over here. Which one do we choose? Over here, right? Because it's the most substituted, and this is Markovnikov, Mark, OH2, most sub, sub. Right, makes sense. And let's see. Last one, Br2, what are we getting? What's getting added? Oh, and this one should have this, by the way. I don't know if you got that, but if you guys didn't, take a second, do it real quick, and here is your answer, right? And same thing as OH, we're just adding two halogens, right? Or I guess Br, sorry, right? Br, and that's it. And actually, this is anti, right? So if anything, we should have a dash or a wedge here, or like a dash over here, right? Showing that they're opposites. So if that was an answer choice, that's the best answer choice because they're opposites, right? So anti-addition, right? So things like that. Very, very simple, right? Nothing too crazy. And yeah, you just follow the reactions, right? Again, follow the anti, the sin, anti-mark, Markovnikov rule, right? So let's do a couple more. Just a different, just a different format of asking the question. Reactions. Okay, so we have, let's see, I think we're in three. So now we're looking for the, what's it called? We're looking for the reagent. CH2Br, so we're looking for this. And then last one, we're looking for the reactant. Reactant. Okay, so There, nothing too crazy. So pause the video and tell me your answers. So for the first one, you guys should have gone what? Something that will make um an alcohol, right? And a Br. So you guys should have gone Br2H2O, right? And again, the HO went to the most substituted, right? HO, most substituted, mark. Mark's rule, right? Most substituted. So what about for this one? This one made both these 50-50 racemic. So, and this one, this kind of curveball, I kind of threw this at you, but this is just a regular elimination, right? Elimination, reaction, and they're pretty much just asking you, and what have we been talking about all this time? Alkenes, right? And to eliminate alkenes, get this, and actually it's pretty much the same as this, OH and H2O, right? OH and bromine, I mean. Yeah, they are the same. I just realized that. So they are the same, right? So obviously we'll be starting up with something like this, but this time with a cyclo um pentene, right? So nothing too crazy. Um Again, right? Anti-addition, anti-addition. So very simple. Just follow the rules. Follow the Markovnikov's rules, the new one that we talked about. So yeah. And with that being said, like I said, very short video. That's all there is to it. If anything, preparation of alkenes and addition reactions are the takeaway, the big takeaway. The fatty acids are cool too. So yeah. I hope to see you guys next video. Hopefully that helped. Hopefully that helped summarize the chapter, the lesson. And yeah, we'll see you guys later.